Topic of the lecture today is exponential and logarithmic functions. They're related, so we're going to discuss them at the same time. So an exponential function has this particular form. It's a function f of x equals a to the x, where a is a number greater than a zero, positive number, is called the base. Notice the variable appears in the power. Okay, so the base has to be a positive number. So what we're going to do first is we're just going to discuss what some basic functions look like, exponential functions look like. And they're very nice functions. Okay, so we're just going to follow the same procedure always. Our function rule is f of x equals 2 to the x. So in this case, we took the base to be 2. And this is an exponential function. And the domain is all the real numbers. Okay, so 2 to the x works for any real number choice. We're going to convert the function rule into an equation, and then we'll find all its xy pairs and put them in the solution set. Now I know what the answer looks like, so we'll choose minus 2, minus 1, 0, 1, 2 for the x values. They'll work. My point of this is you'll see that exponential functions are very nice functions. They behave very well. So my equation is y equals 2 to the x power. So we're simply going to plug in the x values, and we can generate the y values. So 2 to the minus 2 is 1 over 2 squared. 1 over 2 squared is, of course, 1/4. Okay? And we'll go to x equals minus 1. 2 to the minus 1 power means 1 over 2. And it's 1/2. Now we'll look at x equals 0. 2 to the 0 is 1. Look at 1. 2 to the 1 power is 2. And we'll look at 2. X equals 2. 2 squared is 4. So we have some ordered pairs that we can put in the solution set. And again, we don't have infinitely many ordered pairs, but 5 will give us a good idea what this function looks like. And again, the point of this section is it's a very well-behaved, nice function. So here's a graph of it, and here's our points, and I just have them lying along the graph, and everything works nicely. I mean, this is a nice function. And we're just going to compare then what the different bases, how the bases affect the function. Okay, and again, I'm just trying to emphasize that there are infinitely many points, but we've only plotted so many of them. Okay, but it's still sufficient. This isn't, again, this exponential functions work nicely. Okay, so that's y equals 2 to the x. Now I want to compare this. You can go about it in the same way. Now notice what I'm going to do here. I'm just going to change, this is very heuristic. I'm just discussing this in character. So I'm changing the base from 2 to 3. So the base is increasing. And notice what happens to the shape of the graph. Okay, so we're comparing and contrasting. So if I go to base 2, 3, then 4, notice the graph starts out flatter, but then increases more rapidly. So you can see that the base originally starts out on the left growing slower, but then as you move right, it starts growing much faster, particularly for positive x values. So that's a trend we notice. Now if we go the other way, notice the base is 4, 3, 2, and now 1. Notice it really flattens out. In fact, it's just a horizontal line, y equals 1. Right? Because 1 to any power is 1. And now look what happens. If I go to the base that's a fraction, the graph flips. It's decreasing now everywhere, right? So it actually turns over on the other side. Notice that the 1/2 base and the 2 base, notice that these are symmetric. They're symmetric about the y-axis. And you don't have to necessarily memorize any of these things. These are just the characteristics of exponential functions. They all have this nice, smooth behavior. They increase or decrease depending on whether the base is greater than 1 or less than 1. And the rate at which they increase and decrease depend on the magnitude of the base. So notice as the base gets smaller from 1/2 to 1/3, it decreases more rapidly. It comes down faster. And notice again, this is symmetric between the 1/3 base and the 3 base. They're actually symmetric about the y-axis. And again, I go to the base of 1/4 and notice it's symmetric with a base of 4 to 4, base of 4. So they all have these characteristics, and this is what exponential functions look like. Notice that as you increase the base, they tend to swing up on the first and fourth quadrant. For positive x's, they swing up like that. And then as the base increases, it swings this way, right? So as I go from 1/4, 1/3 to 1/2, I go this way, and then to 2, 3, and 4. So it has interesting characteristics. Anyway, this is what they look like. They all go through the point x is 0, y is 1. So it's just they're just nice, smooth functions. Now, how about a function like this? Notice I've added an extra feature here, the x plus 1 in the power. So let's graph this function. So this is 2x plus 1. Now the question is this an exponential function? So take a minute and see if you can answer this. Is this an exponential function? Just compare the definition and see. Right, here's the definition. An exponential function has to have this form, right? So is the one I gave you an exponential function? No. No, it's not. So you could argue possibly that the base is 2, right? You could argue that. But then notice the power has to be for an exponential function, x, not x plus 1. Yeah, I mean, it's just a definition. It's the way the game is played. It's not that it's a huge thing, but it's not, in fact, an exponential function. So, again, as we did with polynomials or anything, learn to follow the definitions. Learn to play the game. So it's not an exponential function. So what is it? It's a good question. Good question. Good question. Well, if you just do the algebra to it, and this is usually the intent of these problems, although it doesn't matter, just plot points. But if you did do the algebra to it, you'd see that it's just going to be 2 times an exponential function. So this is 2 times an exponential function. Well, yeah, that's interesting. We'll see how that plays out, in the graph. So again, these are just features out there. They're not huge, but they're just features. How would I graph it? I would just graph it by turning it into an equation, plotting xy pairs, right? Plotting xy pairs. Put them in the solution set. And then draw the picture. And there it is. Now, the reason that I'm showing you this is, in fact, our graph of 2 to the x plus 1 power is 2 times the exponential function 2x. So notice if you just compare these, right? So it's 2 times the exponential function. See, at every y value, you have 2 times, right? If your y value is 1, you're 2 times. Right, 2 times that. If you go take a y value of 2, you're going to be 2 times at 4. So if you go to 2, you're 2 times at 4. So, I mean, it's just a way of looking at it. It's just simply a way of looking at it. But again, I mean, for me, I just assume apply the xy pairs. If you want to be clever, this is fine, but I don't know. Okay, now we're going to start segueing into, the next phase. Look what we're going to compare here. Here I have the x in the power, right? So that would be associated with an exponential function, the graph of an exponential function. Notice down here I have y in the power, right? Notice the difference. Notice the difference, right? So the x's switch sides, right? And so forth. Now for the first one, notice it's just an exponential. We've already done it. Right? It's a nice function. There's nothing wrong with it. That's not the question here. It's a compare and contrast. So we did this one. Now let's focus our attention here. Okay? So let's just, when you're unsure, let's go back to basics. What's the solution set? It's an equation. Let's find the solution set. So what you could do is put in the x's. What you could do is put in the x's and try to calculate the y's. And that's not very easy, right? We ran into this problem with square root. For example, I mean, it's not easy. You can try it. Okay, let's do a better idea. How about putting in the y's? How about putting in the y's? And then we'll calculate the x's. That's exactly what we did with square root originally way back, and that's why I did that example. Right? So we're defined by an equation, but again, we just need xy pairs that make the equation true. We don't need to put in the x's first. In fact, it's much easier to just put the y's in first and calculate the x's. So when y is minus 2, 2 to the minus 2 is 1 over 2 squared, which is 1 over 4. Right? When y is minus 1, we have 2 to the minus 1 power, which is 1 over 2, a half. When y is 0, 2 to the 0 is 1, and so forth. And so we get our solution set. And then we'll just plot the solution set, right? The graph is representing the solution set on the xy axis, and there it is. Now again, I only plotted 5 points, but this is going to be a nice smooth function. Notice well, we'll compare and contrast. Okay, it's a nice smooth function. So we want to compare these. Now the equation x equals a to the y. Now notice that's different. Before, for the exponential, we had a to the x. So if we have a to the y, again, a has to be a positive number, the base, defines the logarithm, defines this function. So this equation, right, a has to be positive, right, that's our equation we did before, x equals 2 to the y, right, defines a function given by this. It'll be called the logarithm base a. Logarithm base a. Now that's a function. Now again, don't be hung up on this terminology log a. Look, just look at it. Look, just look at it. You need the a in there because the base is a, right? So my a appears in all these places. But see, the log a is just, you can't call every function f. I mean, you can't call the square root function f, and you know, every function can't be called f. So you want to give it a name, and the name that we give this, and I don't remember the reason why anymore, but it's logarithm base a, and that's what you call it. And again, I always like to write this. I always think it's wrong not to write it with the brackets. You wouldn't write f of x without the brackets. And so I like to write log a with the brackets to emphasize that it is a function. And this is how we're going to be using it. I always want you to remember this is in fact a function, and that defined by that equation. Right? So the question is, how do you compute the value y? How do you compute the output of the function? Well, this is what we're going to be talking about now. You have to get your head around this. A function is a set and a rule, right? We need a set and a rule such that for every value x in the domain of the function, so we specify a domain, we can calculate a y value, and the y is the value of the function. So we need a set, the domain. So x will be in the domain. When we define it, we'll define the domain, right? And then we'll need a rule such that for every x in our domain, there's only one value. So if x is in the domain of the set, we get one value, y, right? Y is the value. We need these ordered pairs. Now, any way we can construct these ordered pairs. Look what's on the page. Anyway, think what we've done. We give you an x, that's in the set, and the y is determined by some rule. Now we did this, I said this a long time ago, and I said it was going to get here. Same thing as square root. How about any way I can get x, y pairs here? Light bulb, right? There's an x, y pair on this graph, right? That's the x, y pair. That came from this equation, base 2. So when I put 0 in there for the y, in fact, I generated the x. It doesn't really matter as long as the x comes from a set and there's one and only one y value, right? We're good. So that's where I got that point. So when I write f of x equals y, what am I really saying? F of 1 equals 0. But in our case, right, that's how we compute it, either from the graph or the equation. The function is log, in fact, base 2. So we have log, a is 2 in this case, 1. X value is 1. Y value is 0. And so how did we compute it? We computed it from the equation. So we said that point says log, in fact, base 2 of 1 is 0. Right? That's how we actually compute it. Let's look at another point. So I got this point from the graph of x equals 2y. That's where it came from. That's where we got this graph. So that says when y is 1, we originally calculated the ordered pair by calculating then the x value too. So we have the ordered pair. And again, we have f of x equals y. We'll just plug in the values. We have the x values go there. And the y values come out here from the ordered pair. And then we calculate log 2 of x equals y. So log base 2 of actually x of 2 is 1. That's what that ordered pair says. And we have that. So clearly every point on the graph will allow us to evaluate the function. That's the point. Every point on the graph of that equation allows us to evaluate the function. This is exactly how the square root works. So we're going to use this equation in order to define our function. And we're going to work out examples. But that's the connection. You can't just plug into this function. You have to use this equation or the graph to find its values. And so we have a set called the domain, right? And if you look over here, what's the domain? It's going to be the positive numbers. So our domain is going to be, in fact, for the log function, positive numbers. So that equation defines a function, which we call the logarithm, base a, and there's the graph, and that's how you get the xy pairs. They satisfy the equation, and that's our function. So we're going to try putting this to use. Okay, here's just some notation. If you just don't write the base, you mean log base 10. Since log base 10 is kind of common in some ways, if you just drop the base, you have to understand it's log base 10. That's the convention. Okay, so when you drop the base, you mean log base 10. If the base is e is a number. E is a number like pi. It's the natural logarithm. So it's like pi is 3.14, right? Irrational. E is the same thing, only a little less than 3. It's just about 3, right? It's just about 3. So if you don't specify the e and you just say ln, you mean the natural base. Okay, so that's how it works. So before we go further, let's evaluate some particular logarithms. Let's see how we calculate the values. Okay, so here's just some examples. Okay, so let's take a look at these. So we'll work these together. I hope you'll work these with me. Let's look at the first one. Okay, let's look at the first one and see what we can do about it. So we have log base 2 of 8. Okay, now how are we going to evaluate that? Well, all we have really is our definition, right? We have the definition that says if you want the xy pairs here for your function, you have to get them from your equation. So let's use this. We're going to always use this in a very organized way. Okay? So in shorthand notation, I'm just going to write that definition like this. Log base A of x equals y means, so the equal sign is an equal for equations. It means x equals a to the y. So I'm just summarizing that definition up there in this kind of shorter notation so we can use it. So I put that definition up at the top. Now let's just look see what we have right here. Can we just plug in here, right? So you can see already we're going to just pair everything up. And then work to the other side. Okay? So let's match up. I want everything to match, so I'm going to say log base 2 is my function of 8. And we're going to find y. Right? And we know it's going to be this. Now look, I've just plugged it in. So x is 8. So you just follow the path around and you get x is 8. Notice 2 is a. So go over on the definition, that's a. And that's your 2. See how this is working? And then we want to just find the y. Trace the y all around the thing, and that's what we're solving for. So we've converted our logarithmic evaluation into an exponential function where the variable is y. Now the question is, how do you solve equations like this? Exponential equations. How do you solve this? Well, it turns out what you need is the same base. Now, one side will have the variable, the other side won't. And your variable to be an exponential equation will be in the exponent, in the power. So that's your base. Your base is 2. Now the challenge is you have to write 8 as 2 to some power. You have to write 8 as 2 to some power. Now how are we going to do that? Well, I mean, you just have to basically guess, right? So I have it over here, and I'm just going to list out some choices, and we just have to see what works. So if y is 0, we have 2 to the 0, that's 1. And the question is, well, is 8 2 to 1? No, it doesn't work. So that's not a good choice. How about take y equals 1? Then notice we have 2 to the 1 over here. Notice we're trying to get the power that gives us 8. That's what we're trying to do. That's 2. And no, that doesn't equal 8. We want it to be 8. No. See, we're trying to find the power. How about if we take y is 2, the power to be 2. Notice 2 to the 2, that would say the power is 2. That's 4. And again, that's not 8. So if we take the power to be 3, 2 cubed, okay, 2 cubed is 8. 2 cubed is 8, and that's what we want. So our power, right, our power has to be 3, because 2 cubed is 8. Now I know this is an easy one, but in general you'll have to guess. So once you have 8 written as 2 cubed, you just equate them, y equals 3. And that's how, then we're going to put that back. And that's our y. That's log 2. Log base 2 of 8 is 3. Now let's try some others, see if you can. Here's this, log base 9 of 3. Okay, let's try that. Let's try it. So the first thing we want to do is we want to understand, put it in the template of the definition. So we want to convert our logarithmic form into the exponential form. All right, so we're just matching everything up. So we want to find y, right? Just match everything up. And notice, again, I'm just going to basically cut and paste everything. So x is 3, just follow from the definition. It means there's a 3 here, right? That's what that means. 9 is your base, right? 9 is your base. right? And then we want to solve for y, okay? Now how to do that? Give it a try. If you haven't done it, pause and see if you can do it. Okay, I'll continue. So this tells us that 9 is the base. That's what this is telling us. And we need to write 3 as 9 to some power. Right? That's what we need to do, and we need to guess. I mean, you may know it, but we need to guess, generally. Okay, so we need the power. Okay, let's go over here. So I need a power here. And I have to get 3. So I'm going to put in the y, and the output of this has to be 3. So I'm going to guess these, 0, 1, 2, 3, 4, right? I'm just going to guess. I mean, if you don't know anything, just start and go. Okay, if you put 0 in, 9 to the 0 power is 1. That's not good enough. I need it to be 3, right? I need it to be 3. So that doesn't work. How about if the power is 1? 9 to the first power. Well, that's 9. Now that's not right. We need it to be 3, right? We need it to be 3. That's not good. I mean, you get frustrated, right? How about guessing a power to be 2? Plug that in there. 9 squared, 81. I mean, that's just getting worse. You guys are just getting silly now, right? We need 3. You do power of 3, so 729. We're clearly going the wrong way. We need a value of 3, right? I mean, what we're doing is fine, but we have to start thinking a little more now, right? So I need 9 to some power gives me 3. So 3 is in between 0, right? 0 gives us 9 to the 0 power is 1. And 1, because 9 to 1 power is 9. So 3 is between those two, right? The power is y, right? So we need a power between 0 and 1 1/2. Can you think of anything? Once you start seeing it, you can see it. Can you see anything? It's got to be between 0 and 1. Light bulb. How about, okay, you want something between 0 and 1. How about trying a half? A power of a half. It's between 0 and 1, right? So let's give that a try. 9 to the half, 1 power is the square root of 9. That's what a half power means. Square root of 9 is 3. Yeah, the love. Right? So that's what we needed. So my power here is 1 half. And so you equate the powers, and y is a half. And I plug it back in here. That's my y value. So log base 9 of 3 is 1 half. Okay, so again, it's a bit trial and error. Now, why don't you guys try to run all this through? Pause it and see if you can do this. This is more straightforward. Okay, let me jump in then. So if you haven't tried it, really try these things and you'll get it. So I'm going to put it in the template, right? I have my definition. I have to make all the pieces fit. So what I want to do is convert my logarithm to an exponential equation. So x is 1, right? X is 1. My base is 6. And then, of course, the y is the power. Now notice my base is 6, right? Because my power is y. So my base is 6. So I have to write 1 as 6 to some power. I have to write 1 as 6 to some power. First try, 0. You guess 0. 6 to the 0 is 1. And that's what we need. So notice 6 to the 0 is 1. So y equals 0. Y equals 0. And there you go. Okay, so I mean, that's good. How about this one? Log base 8 of 8. Try that one. See if you can do this one. Okay, let me jump in. Here's what we want. Log 8 of 8. I put it in the template. right? Put it in the template. So we come over here and we see that if we take the power of 1, y is 1, we get 8 to the 1 is 8, and that's what we want. So 8 is 8 to the 1, so y is 1. And that's it. We figured that one out. Now, this last one's a bit tricky, so give it a shot. It's worth doing even if you get it wrong. Give it a shot. Give it a shot. I'll start in a minute. Well, I'll start when you're ready. Okay, this is what we're looking at. We put it in the template, right? And we're looking to solve for y. So I'm just plugging in our base is 10, our x value is 0.01, and we need to find y. So, can you pick a value of y such that 10 to the power is 0.01? Again, if you just begin somewhere, right? So if I take y to be 0, 10 to the 0 is 1, right? If I take y to be 1, 10 to the first power is 10. If I take y to be 2, 10 squared is 100. And you can see this is not going the right way. I mean, you're not going the right way. So we need to turn it around. We need 0.01. So what are we going to do? How about that? I mean, there's nothing that says y values can't be negative. X values have to be positive, but not y values. It works. Mind blown, right? You just didn't see that coming. So how about that? 10 to the, once you start seeing it, you get the jokes. 10 to the minus first power is 1 over 10, which is 0.1. And you see what's happening now, right? We're getting much closer. This is the correct direction. So if we try minus 2, 10 to the minus 2 is 1 over 10 squared, which is 1 over, right? 1 over 100, 0.01, right? And it's not a trick, it's just something you're probably not expecting, right? The x values have to be positive, that's the domain. But the y values can be anything. We're guessing the y values. Now, once you see that, it's not a trick, it's just, you know, once you see it, then you're fine. So the y is minus 2, and we plug that in there. So now we know how to evaluate some of these functions. So now that we know how to evaluate functions, let's go back and revisit this graphing problem again, right? We did it as an exponential, but now let's do it as a graphing problem. How do we handle a problem like this? Okay, how do we do it? We'll just go with the regular way. Remember, for your logarithm, the x values have to be positive, right? So you can't plug a negative value or get a negative value for x, right? So just to let you know, that's going to play out later in what we do. So the next thing, I want to convert it into an equation, right? Convert your function rule into an equation so we get x, y pairs. Now again, the point of this is you can't directly deal with this. So you have to convert, convert it to the exponential equation with the variable y, right? With the power y. So remember, y equals log a of x is this equation. The exponent, the power is y. So our base in this case is 2. So now we have an equation. And we can go about plugging in y and determining x. This is how we started. So for the solution set, right, I'm going to get the x's from the y value. So I'll plug in the y values, and we did this already in the beginning, and I'll just calculate the x values. And that gives us our ordered pairs. And once we have our ordered pairs, now again, there's only 5, but these are nice, smooth functions. Once we have our ordered pairs, we can then attempt, I just condensed the information on the left. We can graph our function. So, I mean, that's the idea. Okay, but the key to this is, of course, converting to the exponential form there. Okay, that's the key. And notice in our graph, it just works out that our x values are positive. Yeah, now we've got this. Now, here's what I want you guys to try. There's a feature here, and again, if you try it and you don't get it, you'll learn something. So give this one a try. Try to follow the same procedure. Okay, the difference, of course, here is that I have x plus 3, and you have to be a little careful. Again, there's no tricks here. You just have to be careful how you do it. Okay, let's look at the solution. So in this case, and now this will work out, but I want to remind you, x has to be greater than minus 3. Why is that? Well, because whatever goes in there, right, whatever goes into that box has to be positive. Right? That's what logarithm, whatever goes into the box there has to be positive. And if that's positive, that says x is greater than minus 3. Again, it'll work itself out, and you'll see how it comes out in a graph. But, I mean, be aware of these things. I mean, for the logarithm, whatever goes into the logarithm has to be a positive number. So if x plus 3 goes in, x plus 3 has to be a positive number. All right. What do you think about this now? We convert to the equation. Now, this is the step. Can you convert this using the definition into the correct exponential form? Give it a try. If you haven't done it, give it a shot. All right, let's see. Now, here's my definition, right? I have y equals log ax. It's a little misleading. So what do I get? 2y equals x plus 3, where did that come from? Okay, we have to, when you really write the definition like this, remember, the x and the y are just boxes, right? They're variables. We talked about this in functions, and if you're not careful, you get caught up. So when you write log a to the x, you really mean this, right? Like I said before, x is really a holding place. It holds whatever goes between those brackets. So whatever goes between those brackets, right, and y is whatever goes over on that side of the equal sign. That's what the notation means. The x and the y are just boxes. So if x plus 3 goes into this box, x plus 3 goes into that box, right? And for y, well, y is just over there, so y is the same, okay? But, I mean, you could have a change on the y side as well. So be aware of that. It's not a trick. It's just you have to understand. When you write out the rules, the x and the y, they're variables. That means they're holding. Something has to be placed in there, in the variable, right? It's a box. So this is the exponential equation I want to solve. Right? dx plus 3 comes from here. Okay? So my base is 2, and I'm going to the y power. My base is 2. What I'm trying to point out here is there are ways to do this. Look, if you want to do it, you don't have to necessarily go through the definition. You get it pretty quickly. Let me see if I can find out where I'm trying to go. To the 2y comes from, okay? The 2 is there, and raise it to the y power, right? 2 is there. Raise it to the y power. That gives you the 2y. That's what I'm trying to say. And whatever's in the brackets here just gets pulled down. So, I mean, that might, that's kind of how I think about it. It's the definition, but it's 2 is the base to the y power gives you that. And whatever's over here just comes out. I mean, it is the definition, and that's kind of how I just think about it. If you're comfortable with that, it's okay. Okay, so I'm going to evaluate the x's, right? I need the x's. So what I want to write this is so if I put in the y's, I just get the x's out. Right? That's all I'm doing. I want the x's out. So that's going to give me the x's. I mean, this is a little tricky. I mean, the first time you see this, or any of these types of problems, they're a little tricky. But after you've walked through this, you'll be fine. I'm going to guess the y values. Now, I took it a little different, -1 to 3, because, again, I know the answer. But again, if you just picked, you might have to add another point. So notice I'm just evaluating it. 2 to the minus 1 is 1/2. 1/2 minus 3 is minus 2.5. 2 to the 0 is 1. 1 minus 3 is minus 2. 2 to the first power is 2. 2 minus 3 is minus 1. And so forth. So I have my solution set. I just plot points. Fine is enough. It's a nice set. And here's my graph. So all the information is just condensed on the left, and my graph is here. So it's a nice set. I mean, it's a nice graph. It's nice and smooth. It just has these shapes. Notice the x greater than minus 3, it comes out because we plugged in the y's, but notice all the x values are over here. They're all, right? They're all upstream, all to the right of maybe minus 3, right? They're all to the right of minus 3. Yeah, we're feeling it. We can do this. So in this section, it was a bit long, but you should be able to graph an exponential, and you should be able to graph a logarithmic function like we did. And you should be able to evaluate the logarithm of a number, like we did some of those, the log of, base 10 of 0.01 something, for example, or log base 8 of 1 or something. I mean, you should be able to do those, the logarithm of a number. So those are the two things you should get out of this section. Okay, good luck with that.